Hi, in this tutorial, we're going to be solving problems on Newton's second law, specifically basic problem solvings. If you're looking for harder physics problems, especially the ones with kinematics combined with Newton's second law, you're in the wrong video. This is really just a sigma F equals ma kind of stuff, and I'll be having a separate video for more complicated Newton's second law problems. Anyway, let's get started. So for the first problem, a worker pushes a 35.0 kilogram box along a smooth level floor by applying a constant horizontal force of 18.0 newtons. Assuming negligible friction, what is the resulting acceleration of the box? So first, let's write down the given, starting with the object. So there's a box and it's 35.0 kilograms in terms of mass. And then there is an applied horizontal force of 18.0 newtons, and we're going to assume it's in the positive direction. So that's the applied force, or F sub A. Now take note that the friction is negligible, meaning to say it's too low, it can be disregarded because the floor is very smooth, it's level. So there are no other forces acting along X but that applied force. And then so let's write down the magnitude. And then, of course, there are also vertical forces acting. Like there's also weight, there's also normal force. But take note that those forces obviously just cancel each other out. So they don't have any contribution to the acceleration of the box. And the acceleration is presumably horizontal, okay? Now, the required to find is the acceleration along x, or a sub x. And then the solution here is Newton's second law. So this is just the sigma F equals ma. I just added the subscripts x just to be more specific that the acceleration here is happening along x because that's where the net force is. And then again, we're solving for acceleration. So in that case, you have to divide both sides of the equation by mass, because if you do that, you're going to be able to cancel mass on the right side and you will be left with acceleration along x. So this is our equation. And then take note that the summation of forces along x is actually just equal to the applied force. So if you look at the scenario, there's only a single force acting along x since friction is negligible. And that in itself, the applied force itself is the summation of the forces along x, or that's the net force along x rather. Then we plug in the given in our second law equation. So that would be just the applied force, which is the net force also. It's 18.0 newtons, and then the mass is 35.0 kilograms. Now you might be wondering, Miss, how are these units gonna be playing out? So remember that 1 newton or a newton is equivalent to kilogram meters per second squared. So newton is just a special name for this specific derived unit, just to give honor to Isaac Newton. And then if you look at that, you can actually cancel kilograms and you will be left with meters per second squared as your unit for the final answer. So the final answer is 0.51 meters per second squared. So it's that simple. And yeah, take note that if you evaluate the answer, it looks reasonable, not too high, not too low, because usually, like if you're talking about cars, the acceleration could go about 3 to 4 meters per second squared. But this is only a box, so I think that our answer is just reasonable. Next item, number 2. A box rests on a frozen pond. If a fisherman applies a horizontal force with magnitude 48.0 newtons to the box and produces an acceleration magnitude 3.55 meters per second squared, what is the mass of the box? Assume that the surface is frictionless. So again, given, again, there's a box. And then there's an applied force, horizontal. Okay, so we're gonna assume it's pointing in the positive direction. So the applied force would be 48.0 newtons. And then the acceleration that it produces is 3.55 meters per second squared. So that's our acceleration along x. And then take note, we're aware that there is weight acting downward and there's normal force exerted by the surface on this box. So there's normal force as well. But these vertical forces just obviously cancel each other out. And our concern here is just the acceleration as well as the force acting along x. Okay? So the required to find is mass, that is directly stated in the problem. And for the solution, obviously, this is a second law problem because it's obviously asking us to relate mass and acceleration. Mass, acceleration, and net force rather. Okay? Next, take note that mass is equal to net force along x over acceleration along x, because we're going to have to divide both sides of the equation by a sub x. And this is what you're supposed to get. Next, take note of the fact that we only have a single force acting along x, so the applied force in itself is automatically the net force along x because it's just alone. There's nothing to add it up with. Okay, substitution. So again, since the net force along x is nothing but just the applied force, then that would be 48.0 newtons divided by the acceleration of the object. So that's 3.55 meters per second squared. For the cancellation of unit, again, recall that a newton is equivalent to kilogram meters per second squared. And you can see here that meters per second squared can now be cancelled, leaving us with kilograms as the unit for our final answer. So our mass here is 13.5 kilograms. Of course, last step in problem solving is to evaluate if our final answer is reasonable. So 13.5 kilograms looks reasonable for a box or for a fisherman to be able to accelerate a box because it's only 13.5 kilograms. So yeah, sensible. It's not too high, not too low. Next, item number 3. How much tension must a rope withstand if it is used to accelerate a 1,250 kilogram car horizontally along a frictionless surface at 1.24 meters per second squared? So for the given, there's a car, but of course, normally in free body diagrams that we've been drawing here, we just use box to represent the object, regardless of what it is, even if it is an elephant or what. And for this object, for the car, we have 1,250 as the mass in kilograms. And then we are looking for the tension force that is that needs to be exerted on this car to accelerate it at a certain value. So that would be represented by this rightward arrow, and letter T stands for tension. So, and then we have vertical forces, weight, and normal force that we don't really care about because our concern here is obviously horizontal motion. And then acceleration of that car along the x-axis is 1.24 meters per second squared. And then required to find, of course, we're solving for tension force along x to be more specific because that is directly stated in the problem. Take note that you can also consider sigma fx as your required to find because there are no other forces acting along x. So the tension force that we are trying to solve for would also automatically be the net force acting along the x-axis. So you can also consider this as the RTF or write that as an RTF. Solution. Of course, Newton's second law, where the summation of forces along x is just the tension force that we're looking for. Let's plug in the given. So this is the mass of the car, and then this is the acceleration of the car. So if you multiply that, you're supposed to get 1,550 newtons. For the unit, just remember that whenever you multiply kilograms by meters per second squared, you will come up with Newton because that's the equivalent unit of Newton in if you express it without this special name. So that's our final answer. Reasonable. That's a strong amount of force, but of course we're talking about a car. It's the tension force that will act along the rope that will pull a car. So that's a sensible value. Number 4, a 1,500 gram box is pushed across a frictionless surface with a force of 4 newtons. What is the acceleration of the box? So let's write down the given. There's a box again. It's just all boxes. So the mass of the box is 1,500 grams. And then there's a force acting on the box that is 4.00 newtons. So that's our applied force. Okay, let's list it down in here. And then there are also vertical forces acting on the box. We have weight, and then we also have the normal force. And again, we don't consider them in the analysis because they don't really cause acceleration on the box. We're just concerned with the acceleration along x because that's where something is going on. There's a net force in there. There's an unbalanced force. Required to find, of course, acceleration along x as directly asked in the question. And then conversion. Miss, why is there a conversion? Here's the thing. You have to take note that the unit Newton is kilogram meters per second squared, as I've been mentioning in the previous items. And because it's equivalent to kilogram meters per second squared, whatever mass you have in your problem, it has to be in kilograms, okay? So take note that we're gonna do conversion so that our mass in kilograms will be, our mass in grams will be in kilograms, okay? So for the conversion, we have 1,500 grams as our given. And then you have to multiply that by 1 kilograms over 1,000 grams simply because 1,000 grams is equivalent to 1 kilogram. So by multiplying it to this conversion factor, you can actually cancel grams, and then we will be left with kilograms as our unit, okay? So 1,500 divided by 1,000, you're gonna have 1.5 kilograms. So this is the mass value that we're gonna use in our equation once we solve. So for the solution, again, Newton's second law, because obviously we're just relating these three variables in here. And then the acceleration would be sigma f sub x over m, because we're going to divide both sides by m, or mass, if you want to solve for acceleration. And then again, take note that because there's only one force acting along the x-axis, which is the applied force, that would automatically be the net force along x that we are referring to in our second law equation. So if you plug in the given, the net force along x is our applied force given, 4.00 newtons, and then the mass of the box is 1.5 kilograms. Be careful with the substitution part. Again, we have to use the mass that is expressed in kilograms, and that is because 1 newton is equivalent to kilogram meter per second squared. So because of that, using the mass in kilograms will allow us to cancel kilograms, and we will be left with meters per second squared as our correct unit for acceleration. So that's our final answer, and it looks reasonable. So that's it. It's pretty easy. Let's move to item number 5. So a 10.0 kilogram box is being pushed to the right across a rough surface with a force of 20.0 newtons. The force of friction opposing the motion is 8.00 newtons. What is the acceleration of the box? So let's write down the given. There is another box. It's the fourth box, I believe. What are these boxes for? Mystery boxes. So the mass here is 10.0 kilograms. And then there's an applied force. It's being pushed, right? So it's an applied force, F sub A. And then that is 20.0 newtons. Let's list it down. And then as opposed to the previous problems where there's always just one force acting along our axis of concern, this one has friction acting on it. It's 8.00 newtons. So that's a leftward force. And then we're going to write it in here. So friction force, or F sub F, is equivalent to 8.00 newtons. Miss, why did you put a negative sign? It's positive in the problem. Well, be careful with that. It's very normal in physics problems to give all the given variables as positive values. But when you are listing down your given, especially when you're doing substitution, whenever you have vector quantities, you have to be very careful of the sign conventions that you are using. Are you applying the right sign convention? Because in this case, if our applied force is positive, let's say, for example, here, we take the positive direction as the direction of the applied force. That's our assumption, or that's what we want to set. Then obviously the frictional force has to be opposing the force that we are applying, because that is frictional force. It's the resistance in the motion of the object. So if applied force has been set to be positive, we're gonna have to set our frictional force as a negative force. So it's in the opposite direction, resisting the motion of the object, okay? It's that simple. And then again, we have the vertical forces. We're putting them in the illustration just for the purpose of making the free body diagram complete, but we're not really concerned it in terms of problem solving. And then the required to find is the acceleration of the box along the x-axis, obviously, because it's actually pushed sideways. And then for the solution, we're just gonna use the equation for second law. And then take note that to solve for the acceleration of the box, again, obviously, we're just gonna have to, we're gonna divide both sides of the equation by mass, because that will allow you to cancel mass on the right side, therefore isolating acceleration. So this is our equation. Now take note that we actually have two forces acting along the x-axis, so we're gonna have to express sigma f sub x as the sum of those two horizontal forces. So there we have it. So there's nothing bloody in here. We are just stating that the sum of the forces along x is just equal to the applied force and the frictional force summed up together. Okay, so again, the sigma fx in the equation is the summation of the forces along the x-axis, okay? So that's gonna be applied force plus frictional force. Do not forget to put a negative sign for frictional force, because that is in opposite direction as our applied force, okay? So that's it. And then next, we rewrite this equation into this. There's nothing bloody. We're just saying, we're just replacing the sigma fx expression from here with this expression, okay? Because those are the actual given variables in our problem. We're not directly given sigma fx, but we are given the forces we need to add so that we know sigma fx, okay? Next part is the substitution. So applied force is 20 newtons plus the frictional force, so that's negative 8.00 newtons. And then for the mass, we have 10.0 kilograms. So the final answer here should be acceleration along x is 1.2 meters per second squared. So that's actually it. It's pretty simple. Again, those are just basic problems. And then as a general guide for solving basic problems on Newton's second law, make sure you understand the problem and then draw a free body diagram, especially if your teacher requires you to do that. The free body diagram usually requires, the free body diagram allows you to like understand the problem better because you get to see what are the forces acting and the relative directions as well, okay? And then write down what you know in the problem, so the known variables as well as what you want to solve for, and then apply second law. Just be careful with sigma F. It has to be the net external force acting on an object because it's the sum of the forces acting that determine the acceleration of that object. And then make sure the units properly cancel each other out. You might need to do conversions just so you can see the units coming out properly. So that's all for this video. Thank you so much for watching and have a great day.